Is this dying again? Oh, there we go. That happened a couple of, well, I say a couple years ago. That must have happened like maybe 15 years ago in the town I was in Macomb, Illinois, teaching at Western Illinois University at the time, and there was two gas stations. It was one of the times when the gas prices were really like fairly high for the time. And during about a 12-hour period of the day, these two gas stations were at war. They were on opposing corners. They kept undercutting each other by like a penny. Till it got down to like gas was like 30 cents a gallon. Until finally, like somebody, you had this big line around the corner for people getting gas. It was pretty funny. Finally, somebody at one of the gas stations must have woken up and said, "Oh, wait a minute, we're losing money here."
It's really bad. Like, I have to drive to a different county because, like, the county sales tax on gas makes it worth it to drive to a different county.
I bet you if you actually did the math and you consider how much you're spending in gas.
On the edge, so it's not like.
All right, so it's like 5 minutes one way and 5 minutes another. It just sounds more impressive when you say go to a different county.
Yeah. Well, like, I know other people who do it who don't live right there, but it's like you save like 30 cents a gallon.
Well, 30 cents a gallon, if as long as it's not a real long drive, probably then translates into worth it. But, you know, I always think it's funny when people go out of their way to save like 2 cents a gallon.
Yeah.
And then when you actually do the math, the amount of gas you spent to go out of your way means that you actually spent an extra 8 cents a gallon or something like that. Who knows? All right, so let's talk final exam first. And then, what's up?
All we have to do is show up and get 100 or an 80.
Well, it depends. If you show up to emos and heckle.
You did really well in the final last year.
That's because I studied for like 3 days straight, nonstop.
Well, yeah, and you have to when you blow off the midterm.
And it's like happened the same
You did.
time, too.
I have a.
half did.
You told me you did.
I like looked up answers and they were totally wrong.
I'm getting old. My memory's way worse than it used to be, but I have a very good memory.
No, like the programming parts, I totally blew off.
Well, that's going to happen anyways, because you don't know how to program.
No. That's why I got put on picture duty at the X on.
Well, are you even a designer?
Oh, I've done Photoshop classes before.
So no.
All I had to do was crop the white out of an arrow. Wasn't that hard?
Yeah, seriously. Who doesn't know how to do that? Sure you do.
Here we go.
You do, because we did that in the Apple Watch class when we had a couple of logos, and I did the instant alpha thing, and the magic wand guy in preview. Yeah, but you're usually on something. Oh, yeah. Let's see. You're switching schools?
Yeah.
Where are you going?
Xavier.
What's there that's not here?
15 minutes from my house.
Oh, so
Skyline
basically
Chili.
Skyline Chili.
Yeah.
Yeah. I'm out of arguments. I'm with you. Are you still doing CS?
Yeah. Their program is really nice too. They have
Yeah, they have a good program.
according to their website, it's 90% job placement in 90 days after graduation.
I bet you we had something pretty similar to that, but we obviously have a much smaller population.
Yeah.
So that's relatively impressive. Let's see. Where was the midterm in here? Well, here, let's just start at the beginning, and I'll most of what's going to be on the final is going to be what started from midterm on, but things before that are fair game, but I'll certainly focus on the things we've talked about since then. Let's look up when the midterm is. 300 final is Tuesday at 10:10 a.m. Sound accurate to everybody? So in this room, Tuesday 10:10 a.m. All right, so you should obviously understand Model View Controller. I don't know if I'll ask a question on it or not, but you should understand it. Similar with activities and intents. certainly be comfortable with linked lists. You might find that there's going to be some additional programming on the final than the midterm. You have a little bit longer to take the test. I'll still design the test to be about an hour-long test, but more questions might be programming questions. Maybe not necessarily full-fledged solve a algorithmic type thing, but certainly maybe manipulating stuff. Spin through a linked list and search for a value, return true if it's there, false if it's not, kind of, little kind of logic puzzles, if you will, something along those lines. Then you'll probably have your traditional, two or three questions that force you to, use some sort of thinking. So I would say be prepared to work with linked lists in that regard. Probably not write a linked list. We've kind of moved past that and are using linked lists now. Let's see. Similarly with stacks, they understand the three different functions and what they're used for. And, if I give you some problem that has you, similarly, maybe search a stack for some piece of information, be able to use the stack functions to manipulate the stack. I might say, for example, write a method that takes a stack as a parameter as well. Let's say it's a stack of strings as a parameter, and searches the stack for the existence of the string parameter that is also passed in. So maybe it takes a stack and a string. Returns true if it's found, false if it's not. Make sure the stack is preserved when you're done. So make sure you haven't damaged the stack. So you'd have to go through and basically keep popping off the stack, pushing it onto another stack, and then ultimately rebuild your stack because you did manipulate the stack as you were searching it. So stuff like that. So understand the difference and be able to do some logical things with that. Binary search trees, understand how they work, understand the idea of everything to the left is either less than or equal to, or that kind of stuff, how it keeps itself in a stored state. The tree traversals, those didn't really show up on the midterm. I think I was right around when our midterm was. So understand those. It would be fair game for me to ask you to write either one of the depth first traversals for a binary tree. So if I said, here's a binary tree, visit the nodes in pre-order order or something like that, I would not ask you to do a breadth first search on the exam. We did that, kind of involved stacks and stuff like that, but I wouldn't ask you to do that on the exam. But be prepared to go through and maybe, given a binary tree, visit all the nodes in this order, something like that. So either pre-order, post-order, or in order. Just one of those, but I'm not going to tell you which one. So, but they're all the same algorithm, basically. All right. So then we start getting into our self-balancing trees, our AVL trees. I probably won't have you do a whole lot of programming related to AVL trees because it's a little bit cryptic programming. But certainly understand the benefits of a self-balancing tree, kind of the process of rebalancing it, first identifying how it's out of balance. And so I might ask you to tell me about what are the 4 ways a tree can be out of balance, something like that. So left, 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 right, right, left, right, right. What do each of those mean? Something like that. So be able to understand what it means for a tree to be out of balance and why we want to rebalance it. I might ask you for the, I actually don't think I would. I probably would not ask you to describe the algorithm of rebalancing a tree, but certainly understand AVL trees and the idea of balancing and rebalancing and that stuff. Let's see. It would be fair game for me to ask you to write, if I gave you a a binary tree to tell me what the depth of that tree is, or what the max depth of that tree is. So be able to write a function that takes a tree as a parameter and effectively traverses down the tree on both sides and ultimately determines what's the maximum depth of the tree. So if the left side is 3, the right side is 6, the max depth would be 6, something like that. So that's more tree traversal type stuff, showing that you know how to do that and understand the idea of a left and right child. Okay. Okay, so then we start getting into some of the stuff we talked about more recently, shunting yard algorithm. So understand kind of reverse Polish, something like that. I might, let's think about how this would work. I wouldn't ask you to write the shunting yard algorithm on an exam, but it might be possible that I would give you the output queue, something like this, and ask you to do something something with the output queue or something like that, and that would be more about traversing and doing something with a list. Maybe I might ask you to go through here and count the number of numbers in the output queue, so that would, in this case, it would be 1, 2, 3, 4, 5, 6, 7. That would return 7 in that case. So a lot of manipulation and walking through linked data structures, linear and nonlinear. It's possible I could ask you a question about shunting yard, kind of what it's for, how does it work. I might ask you to describe the shunting yard algorithm. So instead of writing it, tell me how it works. So dealing with the input queue, the op stack, and the output queue, how do all those things work together, and what are the general rules? I wouldn't expect you to be able to tell me stuff about like the right associative stuff for like the powers and stuff. Just the generalistic algorithm of how do we convert from postfix to prefix. Okay, so the concept of a hash function. It would be fair game on the exam for me to ask you to write a function that takes in a string of any length, for example, and produces a, I don't know, maybe I would say a 64-bit output or something like that, and then have you come up with something that adheres to that rule. So you'd have to come up with your own, ghetto version of a hash function. You can kind of use what we did in class today, if you want, but you'll have to understand what does it mean for an output to be 64 bits or 32 bits or something like that. So understand that concept and how would you convert some string into that value. In not necessarily a mathematical great way, but an accurate, legal way. Also, maybe some of the things I could ask about hash functions is the idea of collisions. What does that mean? So having two values that both hash to the same output. And then kind of in here was also those Bloom filters. So talking about, so I could ask questions about the Bloom filter algorithm. I doubt I'd have you write anything specific to the Bloom filter. I'd probably ask something more about hashes and have you write something kind of hash-like as more of a academic programming type question. But Bloom filters would be fair game. Then more recently, we're going to be talking more about the traveling salesman problem today, but certainly graphs would be kind of the last data structure that I would ask you about. Let's see. I probably wouldn't ask you anything directly related to the traveling salesman problem because we're not going to get that deep into it. We'll talk about it at a relatively high level today, but Certainly being able to traverse a graph and maybe search for a value within a graph um, without any focus on efficiency might be kind of fair game to something like this. Let's see here. Actually, maybe do something. We can actually look at an example of that today. That might be kind of a cool approach. So that could make the exam. I probably wouldn't have you. I mean, last class, in your previous homework assignment, you wrote a graph data structure. On the exam, I probably wouldn't ask you to write a graph data structure. I would say, here is a graph. Write a function that takes a graph as a parameter that has these built-in abilities. And I might show you those built-in abilities in kind of the same way the Java documentation shows you, so you'd have to prove you know how to call them, that kind of stuff. So maybe one overarching thing in the exam is going to be the ability to read documentation and then use those tools to be able to do that stuff. Okay, so exam probably will be 10 questions. Most of my exams are 10 questions. I would say for this exam, at least 5 questions will be programming. So half the exam will be programming, so a little bit more programming than usual. Keep in mind at this point you should have 3 semesters of programming under your belt, so you should be able to show me some competence in programming. I am going to ask questions that are less about really hard algorithms, almost like trick questions, and more about showing me general programming competence. Because this class is going to this class effectively graduates you out of the our programming curriculum and dumps you into our upper division curriculum that relies on the programming stuff. That makes some sense. All right, questions about the exam?
Can there be extra credit question in there?
Can there be extra credit question? Well, I mean, it's fair game if I remember, maybe. Wouldn't be worth like a whole lot of points. I mean, it wouldn't like replace a question. But don't you want to like show what you've learned or be truly tested on the stuff that you supposedly learned so that you know where your strengths and weaknesses are and where you should? Isn't that why you're paying your top dollar tuition?
Yeah, but I think when we do the.
I mean, we can't all go to school just because it's close to Chile. I mean, valid reason. At this exact moment, I have like 20 cans of Skyline Chili in my cupboard at home. I ship it in. I have about 5 or 6 different friends who frequent Cincinnati. Every single time they go, they bring me back like a case. All right, go ahead. You were babbling about something?
No, you were saying don't you want to show what you've learned, but like I can get the concepts. I'm bad at the.
Bad at what?
Writing it,
At who?
at the putting it onto the screen.
So you're bad at like doing what you're supposed to be able to do.
Yeah.
That seems problematic.
Yeah, it is.
Oh. Well, at least we've covered that. So now you have what? Almost a week to study. 5 days. You have 5 days to spend. I mean, you have 24 hours a day. You have to sleep 8 hours. So you have 16 hours a day, 5 days. That's a lot of hours. I mean, you could get at least 70 hours of studying in for this exam.
Yeah.
You can accomplish a lot in 70 hours.
It's pretty much what I did last semester.
So I should keep my expectations low.
Yeah, but I figured it out. I only need like a 60% to get what I want to get in this class.
What is it? What do you want to get?
An A or a B. My parents will let me drive my car to school.
All right, so you need a minimum of a B in just this class or
every class.
every class? Okay. So you need to clear. Is it a B average or a
No,
B in every
I-
class?
I-
Nothing lower than a B. Is a B minus count?
Yeah.
Okay, so B minus or better in every single class.
This is
So-
the class I'm somewhat worried about.
All right, so this is the deal breaker.
So I'm going to be studying that.
Okay, so this class is whether or not you get to bring your car to campus.
Yeah.
Okay, now if you get to bring your car to campus, how does this benefit me?
Then I'll probably go home more often, which means I would have extra meal size, which means I can bring you coffee.
What class are you taking next semester?
I haven't decided that yet.
Are you in any of my classes?
I think I'm in one.
Well, that sounds made up to me.
Aren't you doing like some hardware?
325, yeah. Computer organization?
Yeah, I think I'm in that one.
Okay, yeah, so what time of the day is that? Do I want coffee that time of day? Always bribe the fat guy with food. Well played. It doesn't trump chili from, I mean, I think at 2 different occasions I got chili from him last semester. I don't even know what he legitimately earned, but the numbers become very skewed when food is involved.
Have you ever looked on like Amazon? Because they've got that new Amazon grocery.
Yeah, have you priced Skyline Chili on Amazon? It's expensive. Yeah, they charge like $8.50 a can. I have purchased it from there as out of desperation before. Yeah, but typically you can get like $3 a can from the store or something like that. Yeah, they're not overly expensive down there because they're all over the place. But
You can go to Skyline and eat a meal. They'll fill you up for about $12.
yeah, see, I have a different, I guess, view on what fills you up. Because we go down to Fort Lauderdale pretty often. There's the Skyline Chili down there we go
I
to.
heard it's not as good though.
I have found it to be the same. That one, yeah, at least the one we go to. It's in Sunrise, Florida. But they have 3 different sizes for Skyline. For their chili 3-way normal thing.
Yeah.
So they have like the little, basically thimble, and then they have the medium size, which my wife says is too much food for her. I call that 3 bites. And then you have what they call the large size. What they need is the equivalent of Jimmy John's gargantuan double meat. That's what they need. So effectively a trough of spaghetti with a bucket of chili on top. And then really the real cost of their thing is the cheese. So they put just huge thing of cheese on top.
They make those microwavable Skyline Chili.
Oh, it's like microwavable Kraft macaroni. You can't do that.
Yeah, you can. Those things actually expire too.
I don't think you understand.
Have you had Skyline Chili before?
No.
No, it's.
Exactly.
I got to show you something here. Oh, I just saw there's one in Chicago.
I think it was just the Chicago Skyline.
Oh my god.
Yeah, so this is what they have. But then they also, these are good too. They have their chili cheese dogs. They're like little mini. They make the hot dogs themselves, but they put like so much cheese on top. It's so good. This is just awesome.
Cheese is expensive.
I know.
Ridiculous.
But yeah, this is legit stuff. But hold on, now we need to look at locations. Enter zip code. Find closest location to me. Big money, big money, big money. What, is their website crap? Or is this our, oh no, this is our internet is crap. That makes more sense.
Will the internet ever be upgraded? At least the routers?
I have no idea.
Can you request for it?
Yeah, is that even possible? Like, who's in charge of that?
So we have a couple in Kentucky, a couple in Ohio.
Oh.
I'm not sure I would go to Indiana for chili.
They're like right on the border.
Oh, okay.
It's like right on the border of Ohio. That's how I know I'm getting close to home.
That's the closest from here. Or did you click something?
Yeah, there was nothing in Chicago. Yeah. Yeah, the one I go to is this one right here.
So there's a chance that I might be able to visit my friend who lives in Columbus, Ohio.
Ah.
Should I bring back some cans of chili for you?
Oh yeah, I'll pay for it. Yeah, I don't need freebies, but yeah. The answer is yes.
How much chili would
you realize how like pathetic that sounds? Like you want a 60? Like what would it take to barely
I'm
pass?
trying to do better because chances are I mess up on most of them.
Chances I'll mess up on most
I
of
lose
them.
at least 2 points on each one. Or something.
Okay, so well, hold on, but you never go to Cincinnati. I mean, I don't want like cans of Hormel chili. That's not the same thing.
Just print out a label around.
No, if you've had Skyline chili, you would never. It's impossible to mix them. It's not. It's a whole different texture chili. Yeah, it's different.
Is it like
Chili even have-
It's thinner.
It's amazing.
Yeah, because I mean, it basically used as a sauce to put on top of stuff.
Like spaghetti sauce kind of?
Yeah, almost like that. Yeah. Yeah, I mean, you could, but I don't think it's real common to just sit down and eat a bowl of Skyline chili. You usually are putting it on top of something. It would be good, but you're usually putting it on top of something. All right, so let's get some work done. So no more questions about the exam. We're all good. Okay, we all understand my affinity for Skyline chili.
Yes.
All right, good.
Cool. Alright, one quick thing there, chili. I'm on their website, they got a 30-ounce family size thing.
30. What's how much? But they charge they charge an arm and a leg on their website if you buy chili from them.
Oh, yeah, I was just looking at it.
Yeah, so that's like one serving. 30 ounces of chili. I just make a giant casserole dish, put a whole bunch of spaghetti in there, just dump that chili all over it. Use it for 2 or 3 feedings, just put foil over between them. Yeah, legit. You can tell I've done that before. I have a whole game plan. All right, so I think right at the end of class last time, we had just finished, like I don't even think we tested it yet, right? We just finished getting our stuff kind of together. Let's go ahead and launch our app real quick just so it's running in the background there. Okay, so currently our main activity, when we say generate the graph button, we were doing this with JSON last time, so we went ahead and got our 2 JSON arrays for nodes and edges. We went through and we, for each of our nodes, we grabbed the current node object from that guy, and then we added a new node, passing it the name of the node. So our JSON representation of our nodes basically is just a giant wrapper for a list of names. Then we have our edges. That one's a little bit more interesting. So the next thing we're doing is our list of edges. So we go ahead and grab the current object, which is going to be a JSON object. We figure out what our destination and source node is. And remember, when we build our edges, we're building both sides. So we're building effectively 2 edges for every 1 edge we run into. We find the original source and destination, so the first node and the second node, and then build an edge out of those 2, and then we flip those guys around and build a second edge. Okay. Actually, what's interesting here is couldn't we have? Oh no, we had to do it the other way, I guess. Well, whatever. We didn't actually have to. So we go ahead and we grab node 2 and node 1 as our source and destination, and then we add the edge given the value that we got from our code. Then we flip source and destination around. We could have actually just flipped these 2 guys around up here and used the other one, and then we build our value off of that. So we're getting 2 different guys there. Let's see. So this is source.addEdge. And this one we could have just said destination.addEdge source. We didn't have to search again, but we did. And it's, in fact, we can just fix that, right? Rather than search again, let's just do destination, addEdge source, like that. So we'll find our initial source and destination. We'll add 1 edge from source's perspective to destination with the value. We'll add another edge from destination's perspective to source given the value. So now that guy is in our list of, we are currently doing stuff with these. These nodes are pointers, so they're already in our list of pointers, and that's in our core. So our core has our linked list of nodes, and then within that linked list of nodes, it has all the edges that lead to other places, right? Okay. So now we need to have some way, and let's go ahead and run this. So what was my magic trick? This guy? No, this guy. Okay. So we'll go ahead and run this and just make sure it doesn't crash. I don't even think we did that last time. Okay, we generated the graph. And let's see, we should have, let's look at our picture. So we should have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges and 5 nodes. So let's just give ourselves a cursory look at whether that is happening. So we'll go ahead and say, actually, we can do this at the node level. Here's our add edge, so we'll say system.out.println adding edge, and we'll say this dot name concatenated with an arrow. We'll put in, well, this would be good enough. Concatenated with destination dot name concatenated with open parenthesis concatenated with weight concatenated with closing parenthesis. Let's close this off here. All right, so every single time we call add edge, we're going to say adding edge for this name to destination and the associated weight. We should see 12 of these if all of our stuff was being added the correct way. So let's go ahead and, oh, clicked the wrong one, right? Gotta practice. Okay, so here is this guy. So 1, 2, 3, 4, 5, 6. That was C to B. 7, 8, 9, 10, 11, 12. Looks like it's seemingly doing all of them. Okay, so looks like we have a graph A to B, B to A, 15, A to C, C to A, 9, so on and so forth. Okay, so now let's say that we want to traverse our graph. Looking for what would be a good exercise. I'm almost trying to connect this to something I might ask on the final, just so you have some examples. Let's look at our picture here. What information could we gather? Let's say that we were interested in traversing our graph, finding the shortest path to get to C, this guy. All right, from all starting locations. Let's start with that. So basically, we want to start from any of our starting locations other than C, and we want to find the shortest path. Now, actually, maybe we do this. Maybe we start with this as a first exercise. Given your starting location is node E, what is the quickest way to get to C? Something like that. Okay? And maybe even instead of saying what's the quickest way, show me the list of all ways to get to C that doesn't loop back on itself. You always have to take a path out. Something like that. So we'd like to see it goes from E to D, D to C, and adds those two numbers together, let's say. we'd like to see E to D, D to B, B to C, adds all those numbers up and gives us a value. We like to see E to D, D to B, B to A to C, and add all those numbers out, and kind of just print those when we get to the end of that line, rather than making a determination of which was the shortest path, which shouldn't be a huge deal. All right, so we want to have a function that takes in the name of our starting node and the name of our destination node as a starting point. So let's do that. And we'll write this in core just to keep it in one kind of clean place here. So we'll say static. Let's make it void. We'll just do some printing stuff. So static void, and actually just before I forget here, it's a node, right? I'm going to go ahead and comment out this line so we don't have a whole lot of extra gibberish printing to the screen. So we'll say static void, let's see, find paths, string start, let's start node, string end node, something like that. All right, so the first thing we need to do is we need to grab our start and end node by their name, so we can do that locally here, right? So we'll say node start is equal to get node by name, start node. Node end is equal to get node by name, end node. All right, so now we actually have the physical nodes. We want to keep going and follow every edge until we get to a, until we are traversing to our end node, okay? So assuming we have our start node and thinking about the nature of our graph currently, where when we visually look at our graph here, our graph has, this node links to this node and so on and so forth. But the reality is this node has a list of edges. And in his list of edges, he has exactly one edge, okay? And we're going to follow that edge. Now, depending on what the destination of that edge is, if it's our final answer, we're going to stop, right? If the destination's name is equal to actually we can say if the destination is actually equal to our end destination, we can just compare the pointers for our nodes, then we're going to add the final number and say this was the path, okay? Otherwise, we're going to ask this guy to traverse. So we need to teach our nodes how to search their edges for a, take all of their edges to new paths, something like that, right? But never circle back. So we need to remember where we just came from. That way we omit an edge that takes us back to where we originally came from. All right, and we'll just take all edges off of there. Now, even as we say that, let's think about that logic. Do we have a potential, I don't know if we have a potential problem here. Let's say we're ultimately trying to get to E, and we started at B. Yeah, I think this might show one problem we would have. So we would go from B to A. We would not go back to B because that's off limits, because that's where we just came from. Then we would go from A to C. Then we would not go back to A because that's where we just came from. But now we have been to B. We've been here before. So we really want this traversal to be off limits. Right? Otherwise, we're going to get stuck in a loop, right? Okay, when you read about graphs, one of the things we have is something called a cycle. So if you could just sit here and just keep looping around here and get stuck in recursive calls over and over and over again because you're never actually exiting it. So we really need to have this guy be off limits. Even though it's not where we just came from, as in we just came from A, we don't want to revisit a place that we've previously been to, right? So what we really need to do is in each call as we're traversing, we need to pass along a list of the node names that, or actually let's say the nodes that we've actually visited. That way we have the opportunity to have names that duplicate each other. But we need to keep that compartmentalized on a per node basis rather than keep track of it in our singleton. Because each individual call to each individual recursive call. If we start here and we say, okay, well, so we start off by visiting B. So let's say we build a visit method into our node class. When we visit B, we're then going to, we'll pass in the empty linked list of places we visited, something like that. It'll be a linked list of nodes. Then we're going to say, we're going to visit A, we're going to visit C, we're going to visit D. We'll call visit one time for each of our outgoing tracks, okay, each of our outgoing edges. So remember, one of the reasons that last class we were talking about the traveling salesman problem, and something I brought up is it's really expensive. It's actually a known time complexity problem. That's why we have algorithms for trying to solve it. But I also promise you, the algorithms for solving it are also expensive. None of them are super fast. Just some of them are faster than other ones. And a lot of times the algorithms we use in reality become approximation algorithms. Don't necessarily find the minimum spanning tree that visits all the nodes, for example, with traveling salesmen. Instead, give me a, quote, pretty good spanning tree that visits all the nodes, but doesn't necessarily exhaustively search everything. So you guys read up on greedy algorithms, right? So the concept of that greedy algorithm was effectively saying we're going to make a best guess on which path we should take from here rather than exploring all paths, with the hope that the shortest path leading from here leads us down a path that gives us a pretty good solution rather than the best solution. Then we can decide how many times do we want to iterate over this thing, cutting out paths that we've previously done to ultimately get us to a minimum spanning tree. Okay, but to figure out that minimum spanning tree, to exhaustively, effectively take every path and then compare the voyages is expensive any way you cut it. Make sense? All right, so we're not going to come up with some sort of, in terms of big O notation, in terms of the time complexity of it, it's always going to be expensive. We can make it in physical time happen more quickly by doing it asynchronously through like multi-threads, or actually better, doing it on multiple machines. So if you have maybe a graph in the cloud, so understand our graph data structure here, the structure itself is not the problem, right? The storage size of our graph isn't that big, it's just some text, right? But taking all the little paths and counting up the numbers, that can get expensive. That's the bad part with it. So now, having said that, if we are storing our graph up in the cloud somewhere, and we ask each of our separate machines that are helping us with the traveling salesman problem, for example, and ask each of them just to download their own copy of the graph, that's not that big a deal. This is just data. Traveling salesman isn't a data complexity problem. It's a time complexity problem, the amount of time it takes to search stuff. So we don't need to worry about the amount of storage we have. But in that particular situation, maybe we have a separate computer deal with the graph from each of our starting locations. So rather than having one computer say, well, let me look at everything from A, then let me look at everything from B, then let me look at everything from D, so on and so forth, we have one computer work on A. Simultaneously, we have another computer work on B. Simultaneously, have another computer work on D. And then when they're all done, they come back together and say, here are our findings. Our shortest path, maybe this guy's shortest path that visited everything, had this value associated with this weight. This guy says, well, I had a different value, so on and so forth. And then from there, we can cut down the physical, as humans perceive time, down to a minimum, even though we did the same amount of exhaustive work. Kind of makes sense? This might, I don't know if this is something you'll talk about in your cryptography talk, because you're probably doing it, obviously, from more of a math spin of it, but are you talking anything about what it would take to crack an algorithm in terms of the amount of time and things like that? So, this is like the enemy of cryptography algorithms, is this idea of being able to distribute the work over millions of computers. So if I have a single computer that effectively brute forces guesses at, some famous algorithm, pick your poison, RSA or something like that, and we effectively just keep generating guesses at what the private key is, let's say, it might take 1,000 years. Let's just use that as an example. If we leverage lots and lots and lots of computers, we might be able to drop that down to a minute. Even though it's the same amount of total work that we had to do, we just happen to harness, in an extreme example, 1 million computers to help us do the work, something like that. So distributed computing becomes the enemy of security today, when historically the idea would be that if you had a cryptography only had to be strong enough to make it unuseful. So let's say that the president was sending a secure message to somebody. And this message had something to do with what's going to happen in at some meeting in a week. As long as that couldn't be cracked within a week, you're fine. You're fine. If somebody happens to crack it 3 weeks down the line, that meeting's come and gone, and it's probably already been on the news and stuff like that. So whatever was secret in that message is now public knowledge, likely. But that world has changed with distributed computing, and so that's kind of an interesting. So see, now they don't have to come to at least a part of your because that just covered it. That was the whole thing. What is the specific topic? So I don't have to come. Just as
doing like monoalphabetic ciphers. So
okay.
Substitutions, means.
Okay, so you're talking about the specific math,
Yeah.
the underlying math of that of those ciphers.
Yeah.
Sure, that's good. It's kind of cool. Well, I wouldn't say it's cool stuff from an entertainment perspective, but it's interesting stuff.
It'd be way more fun to do like computer stuff.
Well, they all relate though.
Yeah, they do.
I mean, you have to mathematically show what it would take to, from a hacker perspective, take to crack something. What are the number of what's the number of keys I have to try, or is there? And this really is where a lot of cryptography happens at the math level. Is there a mathematical shortcut we can take? Is there a weakness to the algorithm that we can, instead of having to try every key? Once one key fails, are we able to determine that it failed in a certain way so that we can make other decisions based on that or something? So, yeah, cryptography is a cool thing, but unfortunately, from a computer science perspective, most of our industry experts in cryptography are former hackers who broke into stuff. But at the very least, we've brought them back to the, I guess, away from the dark side or something like that, for utilizing their skills for something productive. All right, so in any case, when we're dealing with time complexity, the more machines you can put on something, the better. All right, but we're going to do this all locally on one machine using recursion. So we're going to visit our first node, and we're going to say, are you the destination? All right, well, the idea is for us, we're not going to be the destination. So we're going to pass him the empty list of nodes that he's previously visited. Then he's going to say, okay, well, I'm going to check each of my edges. Okay, and every single time I take an edge, when I visit A, I'm going to pass along myself, the list containing myself. I'll add myself to that linked list of previously visited places, so that this guy will have that knowledge so he doesn't go back. Similarly, when we go here, but we're always checking, is the place I'm about to go to the final destination? If it is, add the weight and print out the total values, and then you can go down your linked list and actually show the path you went. So let's write this real quick. All right. Is that English? I don't think so. It reminds me of I don't remember what it was. There was some comedy show I saw recently. Oh, it was a movie, a remake of the National Lampoon's Vacation or something like that. Really bad. Okay, difficult, but there was a couple of funny parts, and he rented some this car for the family trip that was, I don't know, some foreign country made car that was not good. It had things in it that didn't make sense. And it had this whole control panel that had like 50 buttons that you didn't know what they did. So at different parts of the movie, they were just trying buttons to see what happened. And one of them made like the car explode. Like, why would there be a button for that? But it had a built-in GPS and it had different voices. And one of the voices that they got stuck on was like a Chinese guy giving the direction. And he always sounded pissed off, just screaming at him. And they were taken aback when they were listening to it. All right, so we're going to say public void visit. So this is when we're visiting a node. So when we visit a node, we are looking for a destination. So let's say ultimate node destination. That's our goal. So here, we'll even call it destination goal. And then we're going to have a linked list of node called prev nodes, something like that. So those are the nodes we've previously visited. All right. So when we visit this guy, if we think about this from the initial call to visit, we're coming right here. So we're going to visit our starting point, our source. Okay. So let's go back to main activity. I'm sorry, not main activity, our core, where we're writing this. So we're going to go ahead and say start.visit end and then new linked list of node, like that. All right, so that gets the ball rolling. We'll start at our starting place. We'll visit the starting place first. Tell them where we're trying to get to end. And then at this point, you haven't visited any place. All right, so he'll get a copy of this. All right, now we need to go through each of our edges. So we're going to say for edge E in this dot edges. So for each of our edges, we're potentially going to visit it. So we're going to ask if E dot, what would it be? Oh, we've made those all private at this point. Generate getters for all of them. Okay. Here. So E dot get destination. If E dot get destination is equal to destination goal, all right, then we have arrived, print out the path and total weight, something like that. In fact, we should also probably have a int running total weight. So then when we first call that guy here, we'll pass it as 0. We haven't had to travel anywhere at this point. Okay. So we'll go ahead and say system.out.println arrived at destination total weight running total weight plus E dot get weight. So that's our last value we have to tack on to that guy for arriving at destination. And then we can go ahead and show them the path that we went. Now, if we're always, so before we write this part, let's go ahead and visit on this side because we need to determine how we're adding the places we just visited to our list. Are we adding it to the end? Are we adding it to the beginning? So we know how to interpret the original guide. I'm thinking we're going to add to the end. So else, if it's not the destination, Then we're going to go ahead and we want to visit E from our current place. So we're going to go ahead and we're going to say linked list of node. Let's see. We'll call this prev nodes copy is equal to prev nodes dot. Do we get a copy? A clone? I don't think that's gonna. We need to make sure we're working with a copy here, because the if everybody's tacking onto the same pointer, then you're gonna have this linked list that has a whole bunch of duplicates in it. We really want each individual call to visit to have their own version of the linked list previous nodes that is theirs, and they're free to change it. Okay, so this will work. Okay, so then we'll say prev nodes copy dot add all from prev nodes, so that copies it all in, and then we'll say prev nodes copy dot add. Says add to the end, whatever. We're out of time anyway, so let's just write this last piece, and we'll add ourself to that list because we've just visited here, and then we'll go ahead and say e dot visit, passing it. Why isn't visit coming up? Oh, this is not e. This is at a node level. So we'll say e dot get destination dot visit destination goal, comma, running total weight plus e dot get weight, comma, prev nodes copy. Basically that. So that should do all the work, and then ultimately what we might want to do is run through our list and show the places we visit in the right order. Something like that. That should be the whole algorithm. Make some sense? All right, I will see everybody on Tuesday, 10 a.m. But hopefully I'll see some of you at the senior seminar presentations before that. But not an EMO's presentation for math. That's off limits, right? Yep, perfect.